Hi everyone, welcome to another video. In this video we will discuss about two-phase flow. So before actually diving into the simulation, it's critical to understand the theoretical foundation behind two-phase flow. In many real-world applications, different fluids come into contact, interact and influence each other's behavior. Two-phase flow refers to the simultaneous flow of two immiscible fluids that do not mix within a single domain. These fluids could be liquid, gas, or even a combination of both. Understanding how these phases interact is essential for industrial users ranging from petroleum engineering to environmental science. Now let's discuss a bit more about two-phase fluid dynamics. In our case, we'll be focusing on air and water as the two phases. Like, these are the most simplest thing we can think. Like, for example, you have a glass of water and let's say you close the other side and try to rotate how the glass will actually fill or how the fluid will move and so on. So air, being a gas, is much less dense and less viscous compared to water, that is liquid, at room temperature. These differences in physical property cause the two fluids to behave very differently when they interact. In fluid dynamics, the behavior of this fluid is governed by the Navier-Stokes equation, which describes how the velocity of the fluid changes due to the forces like pressure and viscosity. In two-phase flow, each fluid has its own set of velocity and pressure fields, but the key challenge is modeling how this field interact at the interface between the two fluids. Let's discuss about the interface. The interface is the boundary between the two immiscible fluids. In our case, between air and water. The behavior at this interface is complex and is influenced by factors such as surface tension, pressure, gradients, velocity field, and also some other factors such as the surrounding of the fluid, how it is influencing the interface, and so on. Let's discuss a bit about surface tension. So surface tension is the force that basically acts on the surface of the liquid and tends to minimize the area of the interface. So if you can think about an easy example in our daily life, so you must have seen water droplets that tends to form like a spherical shaped drop. So that is basically a property of the surface tension that actually helps them to form like a spherical shape just to minimize the energy. Right. So in a two-phase flow system, surface tension do play a crucial role in how fluid interact at the interface. It resists deformation of the interface and influence how the fluids separate or combine. Now secondly, pressure gradients are also an important concept. So pressure gradient is basically the rate of change of pressure in space. In two-phase flow, pressure tends to be different on either side of the interface due to the different densities and viscosities of the fluid. The difference in pressure creates a force that actually drives the motion at the interface. Then let's talk about the velocity fields. This is the most important one. So velocity field can be described or we can describe velocity field basically how fast and in what direction the fluids are moving. In two-phase flow particularly, each phase can have its own velocity field, but the velocity at the interface is typically continuous. The interface moves along with the velocity of the fluid, and this movement is important for understanding how the fluid mix or separate, or how the interface actually change with respect to time. Now when we talk about the level set method, many of you might not be used to this term. So just to introduce you to the topic, in short, it is basically like tracking the interface. So to model two-phase flow, we need a way to track the interface between the fluid over time, right? Otherwise it would be super hard to actually model this kind of system. One of the most effective method for doing this is level set method. In this approach, basically what happens is the interface is represented as a zero contour of a higher dimensional function called the level set function. So the level set function, this scalar function, is defined throughout the domain of the simulation. The interface between the two fluids is represented by the point where this function is equal to 0. the value of the function is positive on one phase. For example, in our case, it could be the air phase, and the negative is on the other phase, that is on the water phase. As the fluids move, the level set function evolves, allowing us to track how the interface changes, shape, and move or even break apart. So if we talk about the Navier-Stokes equation, the Navier-Stokes equation are the fundamental equation of fluid dynamics, as you all might know. They describe how the velocity of the fluid changes in response to force like pressure gradients and viscous stresses. For two-phase flow, this equation must be solved for each fluid, with additional term to account for the interaction between the fluid at the interface. Now mainly there are the two terms that are really important. The first is when we talk about incompressible flow. For most two-phase flow problem, the fluid are assumed to be incompressible, meaning their density does not change significantly over time. This simplifies the Navier-Stokes equation by removing terms related to density changes. Then the viscous force. Viscosity is the measure of the fluid's resistance to flow. In two-phase flow, both fluids have their own viscosity, and this influences how easily the fluid can move past one another. High viscosity fluids like water resist deformation more than low viscosity fluids like air. Then comes the different boundary conditions. In any simulation, boundary conditions are essential for defining how the fluids behave at the edge of the domain. For two-phase flow, typically boundary conditions might be like the no-slip boundary condition, open boundary condition, symmetric boundary condition, and so on. For example, in optics, we generally use perfectly matched layer where the reflections are taken care of and so on. Now when we talk about the two-phase flow level set multiphysics coupling, this is a specific multiphase coupling that handles the interaction between the fluid and the interface. It ensures that the fluid obey the Navier-Stokes equation while the interface is tracked using the level set function. So this is basically the overall physics that is going on while actually solving the two-phase flow problems. So welcome back to this tutorial. Now that we have covered the theory behind the two-phase flow, let's get started with setting up our simulation in COMSOL. So this is the interface. I've just created a blank model. So let's start by creating the geometry. Okay, we are going to use a 2D domain to keep this simple, representing cross-section where the two fluids, for example, here we will use air and water. So let's start by creating a 2D component. So you can do that by going to home and then adding a 2D component. And now with geometry selected, I can go to geometry and click on square. So this is the total outer box that we are creating. Okay, and now we will add a few more features. So we'll add a rectangle, and I just have few of the dimension so that I don't waste much of the time. So I'll write width and height. So this is 0.02, right? And then I'll increase this to 0.8, and we'll again create a rectangle. And now let me make this small. So yeah, and I'll change the X position also. Yeah, these are like two obstacles that we are going to create. Now instead of creating another geometry, what I can do, I can go to square, and then I can basically add layer. So I'll just add a layer. So now if I see, so this is the geometry that we actually built for our model. So now what we'll do, we'll add the materials in the model. So to add the material, what we can do, we can go to material and then click on add material. So it should pop up somewhere here. Then let me open the built-in library and I will add air. So you can see that the property of air is added inside the material. Similarly, I will add water. So it should be here. Okay, fine. So we have added air and water, and again I will add a blank material. You can always add a blank material. It does not mean that you have to use the materials that are defined in the software. You can always use your own material. So I'll just use blank material for the solid channel. That is not required, but it is good to have a good practice to define materials. So for air, I'll select the bottom part. For water, I'll select the top part. Okay, so we're almost done with the material settings. Now let us add the physics interface. So to add a physics interface, you can either go to the physics tab, click on add physics, or you can also go on to the physics tab here. So when you click on add physics, it should pop up the physics tab. And so here, let me explain what we are going to select. So for this simulation, I'm selecting the physics interface under the multiphase flow category, specifically choosing the option of two-phase flow level set and then adding the laminar flow. So let me go to fluid flow, and then inside the multiphase flow you have this two-phase flow level set, and for simplicity I want to study the laminar flow, so I'll click on add to component. Okay, the reason for selecting this particular physics is that we are modeling a system with two immiscible fluids, air and water. The two-phase flow level set interface is ideal for this kind of simulation because it allows us to accurately track the interface between the fluid as they move and interact. The level set method is excellent in handling changes in the interface, such as when the fluid makes, separate or deform, making it perfect choice for this type of dynamic system. In addition, I'm choosing laminar flow because the fluid in this example move at a relatively low velocity, and we are not expecting like turbulent nature, but definitely for accurate depiction you should use turbulent nature, especially in this kind of physics where definitely there will be some kind of a turbulent thing happening. So the fluid flow, the laminar flow interface solves the Navier-Stokes equation, which describes the motion of the fluid, right? And if you are dealing with high velocity or more chaotic fluid behavior, you would need to select the turbulent flow instead. However, in this case, let us proceed with the laminar flow. Okay, so this is the two physics that we are using. So first of all, what we'll do is in the laminar flow, we'll include the gravity. So we'll have the effect of gravity because we are not trying to add any external pressure or like an inlet. Basically, we'll use the gravity and check what is the dynamics that is being followed. So the second thing with that we'll do is we'll add a point, basically a pressure point constraint. So many people don't understand what it actually means. So basically in this simulation we have added a pressure point constraint. This is necessary to ensure that the solution of the pressure field is well defined and stable. When solving field flow problems, particularly in incompressible flow, like in this case, as you can see, we are using incompressible flow. We are simulating with air and water. The pressure field is determined relative to a reference point. So without a pressure constraint, basically the simulation might encounter issues with ambiguity in the pressure solution, as the solver would not know which pressure value to use as the baseline. By selecting a specific point in the domain and assigning it a fixed pressure, typically set to 0 or atmospheric pressure, we provide the solver with a reference. This ensures that the pressure value calculated throughout the domain are meaningful and that the fluid flow behaves as expected. In simpler terms, pressure point constraint help to stabilize the simulation by giving the pressure field at a fixed starting point, right? So think of it like a sea level kind of a thing. So it is like a baseline in terms of pressure. So then we also need some more settings. So we'll be adding a interior wall, right? So in our simulation, we would define a interior wall. This is a crucial feature when we want to specify how the fluid interact with interior boundaries within the model. So as opposed to external walls or the outer boundaries of the simulation domain, the interior wall is used to actually represent a solid structure or partition within the flow domain that divides the different region of the fluid. It behaves like a regular wall, enforcing a no slip boundary condition by default, and of course, like, you can have a different boundary condition. So this basically means that the fluid velocity is 0 at the wall. This ensures that the fluid cannot pass through or slip along the wall, which is important for accurately modeling real world physical boundaries like pipes, channels, internal barriers within a system, and so on. For example, we are simulating fluid flow, a channel, or over an internal obstruction. The interior wall will create a solid boundary that affects the velocity field of the fluid, just like an outer boundary would. It's useful for a scenario where we want to control the fluid behavior at an internal structure while keeping the external boundaries separate, right? So this is the purpose of the interior wall. And so what we are going to do, we are going to select the interior walls. So we'll just zoom in and select these walls. So these are like the obstacles that I created just to visualize the interaction of the two fluid and nothing else. Honestly, this does not add like any physical significance as such. So since this we already had like a external wall, that's why you can see that we are also unable to select it. So COMSOL is smart enough to actually do this kind of thing, since here, as you can see, the wall is already selected. That's why we can't add like an interior wall again in this case. So we are almost done with the laminar flow. Right now, let us check the settings for the level set. So in the level set physics, we have selected all the domain, and if you see that the initial value we have specified for fluid 1, and we'll be selecting the topmost fluid. So in the fluid 2, we'll select this, and now automatically you can see that the initial value for fluid 1 is selected in this domain, right? So what does no flow mean? The no flow boundary condition indicate that there is no movement of the fluid across the specific boundary. In other words, it acts as an impermeable boundary that prevents fluid from crossing it. So by default, you will see that the no flow is applied in the outer region. It is important to note that no flow condition is different from no slip boundary condition, because while a no slip boundary affects the velocity of the fluid, the no flow condition entirely prevents any kind of mass transfer. That's why you can see it's by default is selected in the outer regions. So one more boundary condition that I would like to add is I'll add like a thin barrier, right? So let me add a thin barrier along the same set of sites. So I'll select all these. So as the term suggests, these are the thin barriers that are being selected as the boundaries. So basically the thin barrier condition represents the boundary that act as a very thin, nearly impermeable barrier between the two fluid, but may allow for some very limited interaction. So in practical application, this could represent a membrane or a thin wall in physical system where fluid and other side have minimal interaction or exchange. This feature ensures that while the fluid remain mostly separated, any interface effects such as surface tension or minor fluid interaction at the barrier are still captured. So the thin barrier settings helps in scenario where complete separation isn't realistic, and some interaction between fluid is expected, such as through a porous medium or a thin layer. So now let's discuss the multiphysics part, and the most important one. So in our case, we'll be using the two-phase flow level set multiphysics. So we are not going to study the weighted walls, right? So basically in this part of the setup, we are using two-phase flow level set under the multiphysics interface. This option is important for modeling the interaction between the two fluids, right? This coupling brings together two essential physics. The first is the laminar flow. This component handles the fluid flow of both air and water, solving the Navier-Stokes equation to determine the velocity and pressure field within each phase, right? And then we have the level set method. As you can see, the moving interface is the level set. So this component tracks the interface between the two fluids, showing how the air and water interact, merge or separate over time. By combining these two interfaces, we ensure that the movement of fluid affect the location and behavior of the interface. The changing position of the interface in turn affect how the fluid flow in both fluids. If we go to the fluid properties, what we can do for fluid 1, we can select like the material that is the water, and for fluid 2, let's select air, right? These are the two fluid for the two domains. Now if we go to the material and check what are the properties that are being used, that is the ticks beside the material, you can see the dynamic viscosity and density are actually taken from the material that are defined in the software. So we have these two values similarly for water, and then for solid, since it is not being actually used, so it is not basically using any of the property, right? But still we define the material because it's a good practice to define the different materials that are used in the model. So we're almost done with the physics. So we can go to mesh and we can click on build all and see how it goes. So maybe we can select like fine mesh. Even in fine, it shows some errors, like some stressed elements. So let it be, since we are just running a demo simulation, so it will not affect much. But what you can do, you can add like manual mesh elements and add more finer elements here, so that the triangles won't be stressed too much, like, and also keep the element size small. You can choose like a more finer mesh, like the extra fine and so on. That will definitely improve, and you can see there is no error right now, or no exclamation, but we'll go with fine because we want to run a quick simulation, right? So we are pretty much done with the mesh. Now we're going to add study. So to add study, we are going to add a predefined study, right? So we'll right click and click on study. So as soon as we add the study, that is a predefined study, what it does, it adds the two different steps in the study, right? So the first step is the phase initialization step. So this step is critical in setting up the initial state of the two fluid. That is, in our case, we have used air and water before the simulation begins to evolve over time. During this step, basically COMSOL calculates the initial distribution of the two phase within the domain and ensures that the interface between the fluid is correctly defined. This is especially important in two-phase flow simulation, where we need to ensure that each fluid is located in the correct starting region. For example, we want water to start from the bottom of the domain and air to start at the top. No, basically we are doing the opposite. So air at the bottom, water at the top. The phase initialization step makes sure that the interface between air and water is properly established based on the initial condition, and it ensures that the simulation begins with a stable starting configuration. Without proper initialization step, the simulation might start with an incorrect or unstable interface, leading to incorrect result or convergence issue with when time dependent study runs and so on. So the second part of the study is the time dependent study. After the phase initialization is complete, we move to the second step. This step is where the real dynamics of the simulation takes place, right? Over the time period, we specify that in the software, and COMSOL will simulate how the air and water phase evolve and interact, tracking changes in the interface, velocity field, pressure distribution, and so on. In this step, the simulation calculates how the two fluids move and interact as time progresses, giving us the insight into the behavior of the two-phase diagram. And if you plot the result, it will actually show how it is evolving with time, right? So this is the overall idea of the two studies that are being used. So let me explain a bit more about the values of dependent variable. These are generally much less described anywhere, mostly. So basically, in the section of this setting, we are controlling how the initial values of the variable are defined for the time dependent simulation. These settings are important because they define the starting condition of the variable that will evolve over time, like velocity, pressure, and the level set function representing the fluid interface. So let's discuss what are the settings actually mean. So the initial value of variable solved for, so this setting determines how the initial condition of the variable are defined. Here we have selected user controlled. By default it is selected as user controlled, which allows me to manually define or select how the initial values are set up for the time dependent simulation. This gives us more flexibility to ensure that the variables start from a desired state. Now second, we have the method, right? And here we have selected the initial expression. The method refers to how the initial value of the variable will be calculated. By selecting the initial expression, we are basically specifying that the initial value of the variable should come from predefined expression, typically from the result of the phase initialization step, or from the initial condition we set manually in the early stages of the model. This ensures that the time dependent simulation starts with the correct value of the velocity, pressure, and the level set function after the phase initialization step has stabilized and the interface between the two fluids. Then we have the study. This means that the initial value of the time dependent study will be taken from the result of the phase initialization. Essentially, we are telling COMSOL to use the output of the first study as the starting point of the time dependent simulation, right? So this is the overall idea of the study. Then we have the selection. So by selecting, then we have selection. So basically, by selecting automatic, COMSOL will automatically determine the best solution from the initialization step to use as the starting point of the time dependent study. This is the default behavior, and it ensures that the solver uses the most accurate initial condition without us needing to manually specify which solutions to use. Then we have the value of variable not solved for. So for any variable that are not actively solved in the time dependent study, we leave the settings as physics controlled. This means that COMSOL will use the default values or behavior dictated by the physical laws governing the problem, like the continuity equation for incompressible flow or conservation of mass and momentum and so on, right? So this is the overall settings of the study. So we are mostly done, and for the time step, let's study up to 10 seconds, and we can study up to a gap of let's say 0.05. So to save time and to show you the result, what I can do, I can just use a user controlled tolerance. So I've set to 0.05. So we'll have a quick convergence of the solution. So this is just to show you as a demonstration. That is why I'm using user controlled tolerance. So I'll click on compute and see how we are getting the result. So these are the convergence graphs. I hope it converges quickly. Yeah, it's running quite fast, so I hope it should be done in few more seconds. So we'll wait for a few seconds before it gets completed. So after the simulation is done, we'll add the plots, or maybe it will add the plots by default, and we'll see the result. Okay, so it is already 64%. You can see the convergence graph. So it's quite smooth, so that is a good indication that it should converge quite quickly. So it should have the time, so you can see the timestamp. We are running for 10 seconds and it is running quite fast, so the simulation will be done in a few more seconds. And yeah, it should be done now. Okay, so this is the velocity profile. let me just open. So it is plotting the velocity and it is plotting with respect to time. So let me see at 0. Okay, let me increase the time. So let me add a animation, right, and see how it actually goes. I'll select all frame and I'll display each frame for 0.2 seconds, and let's try to play. Okay, so now let's try to plot the volume fraction. So we have a contour as well, and let's select some other time and see how it actually looks. So as you can see, there are different contours of the different parts of the fluid. Now let's add an animation to this as well. So we'll select all frame and we'll again plot it for, let's say, 0.15, and let's play and see how it actually looks. Now this looks quite interesting, and you can see that the fluid is actually flowing down and trying to settle to the bottom. This is just 10 seconds. Now if we run for longer time, it will mostly settle to the bottom, and you can see the contour of the two domain. It's also trying to calculate. Yeah, so this is it. So this is a easier, like a more simplistic tutorial of how to actually work with two fluids. Now depending on the project or work you are doing, definitely you have to change a lot of parameters and settings, but this will definitely give a rough idea how to actually work with two fluid and their dynamics in a particular domain. So if you face error, definitely one of the reason could be the mesh. The second reason could be the time dependent and phase initialization steps, and the other problems could be regarding your settings and boundary condition that you have set up in the model. So most of the time the error comes due to these three settings, and in this kind of study the mesh also plays a very important role. You will definitely get error if you do not have a good mesh settings in your model workflow. So this is it. I hope you learned something. I hope you learned something from this video. If you do, please do like this video and share this video, and do support my channel. If you like this video, do subscribe to this channel, like this video, tell your thoughts in the comment. If you have any question, etc., you can contact me. And if you also like to support my work, you can always be a member of this channel. That will definitely motivate me to create more useful tutorial for everyone. Thank you all and have a nice day.